Hello, in this video I'm going to describe how you can do the PLS modeling using the NIRVA cloud platform and the measurements from NIRVAScan. We had many customers who asked about this, so I thought of recording this video to explain it. So the first step would be to prepare a calibration file and a validation file with measured spectra in horizontal rows and the measured value of the ingredient in the first column. So you need to measure the spectrum from each of the samples, and you also need to find the value of ingredient using an analytical technique. This is important to correlate the spectra to the ingredient value. So if you're using, for example, NIRvascan to measure fat in some food product or moisture, you need to measure that for each sample using an analytical technique such as HPLC. So you would divide all your data into two parts, a validation and a calibration. The calibration typically has about 100 spectra, and you need to have a wide range of values in that file. And the validation typically about one-fifth of that. So, for example, 20 spectra with the same range. So you need these two files to come up with an estimate of the error that your model would provide, so that then you can apply it to new samples that you don't know the values of. So let's go to the next slide, and you see this is a raw data from the NIRvascan. So you need to basically copy the wavelength, which is in this column, column A, and the absorbances in column B. So you have to select each one of them individually, and then you would basically make it copy it in an Excel file with all the wavelengths in horizontal rows. So you can see from cell B1, you would paste all these. We can use the basically transpose feature of Excel to, to paste all these wavelengths. And these are all the absorbances that you can see. So you put them in horizontal rows. And the first column, which is in this case protein, because we are measuring protein in wheat, is the percent of protein that you have measured using an analytical method such as HPLC. And once you prepare these for calibration and validation, actually this is just the calibration. You'll see the last part is 1700 is the last wavelength. The first wavelength is 901. So I wanted to show the full range. So then you need to name this. And the naming convention is it has three parts. The first part is the actual material, which is in this case wheat. Then dash, the second would be the ingredient that you prepared this file for, which is protein. This should be the same exactly as the header of column A. And then the third one could be anything, could be a company name, could be the source, if there's a particular field name or any season name or anything that you want. So this is a three-part name that you provide for the calibration file and also for the validation file. Okay, typically I like to add wheat cal to show that this is the calibration file. So the first name would be wheat cal, and for the validation I would say wheat val dash protein dash company name. Okay, so then after you prepare these two files, you would upload them on the cloud. So how you would do that, you would go to our cloud platform at nirvacloud.ai, and if you don't have an account, you need to register your name. You need to sign in, make an account, just give some basic information. And once you go there, you see this window appearing. Then you would choose analysis, which is boxed in here. And after you choose analysis, you would see this screen. So this screen would allow you to import the data, the calibration and the validation. So you would choose a name for the title that you can see over here. And I would say that you would have to use a cal in the calibration file and a val in the validation file. I'll turn off the video here so you can see better. So you can see that choose your cal file and put in the title any name that has a cal. For example, I chose the name test August 2 underscore cal. So you can even remove underscore as long as the calibration file should have a name of cal, because we need that for later on to be doing the optimization. For validation name, you must put a val suffix. So it could be test August 2 val. And then you would also choose the file here, the file that you prepared. You would upload that, and then you would say upload, basically upload. So once you do that individually for each of the files, then you would see you can go to the profiles, and if you click on the profiles, you see that your calibration file and profile and validation profile, each one containing so many spectra are there. So if you just click on them, then you see these spectra are appearing. So here is the calibration, there's 100, and then if you click on the validation, you see the validation appearing too. And then make sure that there are no strange spectra. Like these should kind of be similar. They're only a DC offset between them. Not all of them are exactly similar, but there shouldn't be a very odd shape there. And if there is, then that's an outlier that you need to remove. And you can go to your Excel file and remove that, and then upload again. So just check your validation, your calibration, make sure everything is okay. And then after that, you need to use the optimization to see for your model what is the best number of components for your model. And you also need to apply SG filter, which stands for Savitsky-Golay filter, to smoothen the data after you do the second derivative, for example. So for this reason, you would select the two. So here the calibration you see and the validation, you would select it, and then you go to the drop down menu and then say get optimized parameter and then press go. So once you do that, the optimization output will give you the best number of components that would give you the least error, and also the window length. So this case is 2 and 13. 2 for number of components and 13 for window length. So let's remember these two numbers, 2 and 13. So next would be, you have to make the PLS model. So you would just go to the menu and click on the add, plus add, and you can select any name for the title. Choose the same number of components and SG filter length provided by the optimizer to fill out the information. Choose the calibration profile and press save. So just to see what it looks like this. So you can see that I've chosen any name, for example, test August to take whatever name you want, you could put in there as long as you recognize that this is the validation, the calibration model you're making. And then I put the number 2, which is the number that was given to me by the optimizer, and the minimum maximum are in the range 950 to 1650. We don't want to use the extremes of the wavelengths from 900 to 950 and 1650 to 1700 because they are noisy and they would deteriorate our models. So we use this, and 2 was the number of components. Ignore the cal spectrum, just check the cal profile, which is right here, test August 2 cal, which is your calibration file. We already had this in our profile. Then also select apply SG filter and put the window length as 13, as the optimizer gave us. Leave the other ones the same, polynomial order, derivative 2, and this mode mirror. Leave them the same and press save. So once you do that, then you already have your SG filter, you already have your PLS model created. We'll check that later. We also have to apply the same SG filter width to the validation profile. So we go to the SG filter and then do plus add, click on that. So we will see this window here, and then we would just choose the validation profile that you can see here. We give it the same name also here, and the window length is 13 as it was given to us by the optimizer, and ignore the cal spectrum, just select this one and then click save. Okay, all the other parameters are the same. So now you can go ahead and view the PLS model. So if you go to the PLS model, which is boxed in red here. You'll see it here, the first entry, and you can go ahead and click on it. It has n equal to 2 and SG equal to 13. And once you click on it, you see it appears here. There are all the data points are here. This is for the model itself. It only uses the calibration model. We haven't applied this to the validation model yet. So it already has a RMSE root mean square error of 0.94, which is 1% roughly, and not that great. R square of 0.43 is at the bottom. This is for the model itself. And then you need to go ahead and apply this model to a validation file. So under apply this model to predict selected spectra, you choose the validation file that you applied the SG filter on. And so this is the first entry in there. And then you have to scroll down all the way to the bottom and say, basically apply this model to this spectrum. And then they will give you the predictions, which is predicted value versus the true value. So all these points become clear. And if you hover your mouse over every point, you see the predicted value and also the real value. So at the right bottom corner, you see there are two scores. The scores are the same as R square. So this score is for the model, 0.43, and then there is this score at the bottom for the prediction. So there are two scores there for the ingredient. So one for the model and one for the prediction. And RMSE is also given here, 0.74%. Okay, so all this data is there. And you can also export the data. At the bottom right, there is a tab called Export the Predictive Result to an Excel file. And if you click on it, it will send it to a .csv file. You have your true values and your predicted values there. And this brings us to the end. And I should also mention that once you establish what is the error, the RMSE error, then you can apply the same calibration file to new test files. So create a new test profile and apply the same model to that test file. But you have to remember to apply the SG filter with the number of components, with the number of points that the optimization has given you to do that test file as well, and then apply that. All right, I hope you enjoyed this video and it was useful. Thank you.